probabilities of the predictions. So usually it is useful to have a model that says, black or white or 1 or 0, like have only the predicted class. But so sometimes it's also useful to also see the probability. So if we have similar, today we'll have a look at a classification example, but even if it was regression, the procedure is very, very similar. So feature engineering is the process of selecting, manipulating, and transforming raw data into features that can be used in supervised learning and machine learning in general. Now, in order to make machine learning work well on new tasks, it might be necessary to design and train better features. So in many situations, we do need feature engineering. It's usually part of the machine learning pipeline. And usually, it's a technique that leverages data to create new variables that aren't in the training set originally. So maybe you can combine a couple of features together, or you can apply something like dimensionality reduction using the PCA algorithm, principal component analysis, and so on. This is a really important step in machine learning, really important for you to be familiar with it. Okay, so it can produce new features, okay, for different types of machine learning. The goal usually is to simplify and speed up data transformations and enhance model performance and model accuracy, or reduce the prediction errors. Like we said before, this is a required step, so this is why I wanted to speak briefly about it. And, a terrible feature can have a negative impact on our models. So usually applying feature engineering and new feature selection and so on is a key step, okay, really important. Feature selection, this is the process of reducing the number of input variables or features when developing a predictive model. Usually we try and reduce the number of input variables to, reduce or cut down the computational cost of our model, and at the same time to improve the performance of the model, so to improve the accuracy or improve or reduce the error of the model, reduce the prediction error. Okay? Normally in feature selection, we have the original features and then we select a subset of them. In dimensionality reduction, we have the original features and we generate a lower number of new features that are combinations of the original features. Okay, so this is for you to know the difference between feature selection and dimensionality reduction. And please ask me a question if you don't understand anything. Send the question via the Q&A, and I'll be happy to help you answer it. So why do we apply feature selection? Normally, they make model interpretation easier and simpler because we have a smaller number of variables to look at. Training times can be faster. We can also reduce the problem of overfitting. And even for software engineering or for software developers, they write less and less code if we have less and less features. We also reduce the risk of data errors or errors due to data. Also reduce data redundancy because in many situations, we can have what we call, for example, highly correlated variables or maybe duplicated variables. And normally, reducing the number of features can help a lot in avoiding those problems. So feature pre-processing in general, usually we have raw data and we want to make it into meaningful data that is possible to be used to train machine learning models, so it can be consumed by models and models can be trained using that data. Usually data in the real world is incomplete or inconsistent. I know this for a fact. It's part of my job. And normally you get courses doing data analytics and the data is perfect and very clean. That's not the case in the real world. So you'll have to be familiar with data manipulation, cleanup, and so on. Okay? There's plenty of pre-processing techniques. For example, if you have categorical data and you want to represent it correctly, then there's a technique called one-hot encoding. If your data is numeric and then your models work well with data, the range of which is between 0 and 1, so you can apply data scaling or normalization. You can also apply standardization, where you subtract the mean of each numeric column and divide by the standard deviation. Missing values are a real-world problem. It's very common, so we'll have to learn how to deal with missing values. Something you decide. There are plenty of techniques to deal with missing values, and it depends on the business case, it depends on the problem that you have. Also, in the real world, especially in machine learning, we have the problem of reproducibility. It's actually a challenge, not really a problem, but in many situations, we want our results to be reproducible for consistency, even for a financial standpoint. If we were to invest significant resources into creating a model in a research environment, but if we cannot reproduce the results in a production environment, then the model can have little benefit. So definitely, we need to make sure that our results are reproducible, and if we don't have that, then it can have plenty of negative effects. So that if we cannot reproduce results, then it can lead to financial loss, wasted time and effort, and unfortunately, the model will not be really useful. Okay, especially if, like we said before, we want to replicate prior results. Otherwise, imagine you have different versions of the same model. If you cannot reproduce results, then it becomes difficult to even compare models and know if the newer ones are better than the previous ones. Here I include several links to really useful stuff about reproducibility. I highly recommend the articles by Soli, Gali, but you can also have a look at the slides here, or about this article by Pete Warden, and so on. Okay, and now when we speak about deep machine learning, we might also want to speak about neural networks and deep learning. So within Python, we have the scikit-learn package. That's the main package for machine learning. But for deep learning, we can also have a look at Keras and TensorFlow and so on. So these are a few useful links. I quite like the stuff here on Machine Learning Mastery by Jason Brownlee. So his stuff is usually useful. The website is generally rich, so I'll leave that for you to go through in your own time. And you make sure that we're doing well in terms of presentation, and you can see my screen. That's good. Excellent. Let's continue. Now, a little bit of comparison between research environment and production environment. I am academic, so I work in academia. I know the research environment really well, and I also work in the industry as a consultant, so I sort of combine the two of them, okay? And usually in academia, things, or in the research environment in general, things can be a lot easier because we don't face customers when we do research, so that makes the environment a bit more relaxed, at least in my opinion. Whereas in the production environment, the model is being used by real-world users, so any error, any mistake can be highly costly. Reproducibility, usually we want it in research, absolutely necessary, but it's even more necessary in the production environment. Usually in research environment, we don't pay much attention to scaling unless required, whereas in production environment, we do need scaling because the number of users can become really large. It can become too much to whatever serving our model, and therefore we need to consider scalability issues. In research environment, we can take our models offline because we're usually researching and experimenting, whereas in production environment, that might not be the case. So you need to know what you're doing. And then, in production environment, we always need to think about the infrastructure. Remember scaling, for example, high availability, load balancing, and so on. And in research environment, we can run experiments. In production environment, because that's the model being used in the real world, there's no time for experiments there. Okay, so you need to know what you're doing when you deploy your model into production. I will come back to Python code, or shall we have it now? Okay, let me just say a few words about production code, and then we'll come back to the Python code. So usually, like we said, we speak about research environments, but in the production environment, the code is designed to be deployed to end users, and there are so many different considerations we need to have. Testability, for example, how we run tests, how we maintain our code, our package, or do we have scalability issues? How can we scale our models depending on user demand? How do we optimize the performance of our model? Oh, can we guarantee that our results are reproducible? So many different considerations need to be looked at when we design production code. So usually in Python, we put things into packages. In Python, we have what we call a module, which is nothing but a Python script or Python file. So a module is a file that contains various Python functions and global variables. It is just a file with a .py extension, and it has Python code in it, whereas a package is a collection of modules. Now, you might find that sometimes people say library instead of a package. Terminology here is fine, okay? So let's use it in a loose sense of the word. Now, this is an example of a professional Python package, and today we'll see one live. So imagine you have your original Python code. It can be a Jupyter notebook, for example, or it can be a simple script, and then you want to package it so that you can deploy it professionally. I want you to pay attention here because this, like I said before, this might be new to some or many of you, and therefore I want you to pay close attention. As you can see, I have the parent folder and then a couple of subfolders under it, one called the model, one for the requirements, and one for tests. So obviously we can put our test scripts here, and then if our work or our model or our Python code requires some packages, we can put them into these requirement files. And then under the model itself, if we have any required configurations or any data, we put them into the data sets, or any config, we put it here. I'll show you what config means. If we want to apply data processing, or when we train the model, if we want to serialize the model and persist it, meaning if we want, for example, to save the trained model, we can save it into a separate folder. Then if we have any configuration we want to do, our pipeline, our prediction, when we train the pipeline, and also we can keep track of the version of our model. And you will see why we split everything into smaller and smaller scripts and configuration files. This gives us a lot of power in terms of maintainability. Remember these points, okay, testability, maintainability, scalability, even extensibility. So if you wish to extend your model, then that's the way to go. I have to say that this is a result of a lot of experience. Some stuff here might be opinionated, so feel free, if you think you can, for example, put files in better places or put code in better places, feel free to do that. But I'm hoping what I'm going to show you today is going to convince you, right? So as you can see here, we have this TOML file, a manifest file, and then a tox file. What these files are, what they're for, is what's coming up. So be patient with me. I'll go through them as we progress. Now, before I go any further, let me take you to my GitHub repo, and this is where I have the pipeline. So imagine now you're in a research environment, you have your data, and now you have prepared a Python or Jupyter notebook where you load the data, split it into train test splits, for example, apply any data transformations, any data cleanup, dealing with missing values, data scaling, feature engineering, feature selection, anything you want. And then now you train the model, you have the trained model, you can persist it or you can save it, you can serialize it, you can use the pickle package in Python or the joblib package in Python. And then in the future, you can, instead of retraining the model, you can reload the pre-trained model and then use it for predictions. So this is research environment. This isn't suitable for production deployment. Okay, this is a bit of explanation. It's on the Titanic data, the well-known data. This is a really powerful package. It's called Feature Engine for feature engineering. Feel free to learn about this package in your own time. It has the same coding style or the same look and feel of scikit-learn. It comes with a large number of really powerful data feature engineering and transformation techniques. Okay, this is really powerful. As you will see, it comes with a large number of examples, or what we call transformers. Okay, it does come with a large number of transformers. It's highly rich. Okay, I highly recommend this Python package if you have not seen it before. Dealing with missing data, data encoding, discretization, dealing with outliers, numerical transformation, create new features, apply feature selection, dealing with date time, data, and so on. Okay, this is a really powerful package. That it's actually so powerful that it might deserve its own course. Okay, so this is how you can install it if you don't have it already. And here we apply some imports. Okay, import, for example, pandas, numpy, maybe matplotlib if you want to visualize something, train test split, standard scalar. We'll apply logistic regression, and then we can have a look at maybe accuracy or area under the curve. Joblib package for saving and reloading models. Pipeline from scikit-learn, so we can put everything into a pipeline. And by the way, for feature engineering, data manipulation, and machine learning pipelines, I have my own course with O'Reilly, again on pipelines already, okay, only. So focused on data engineering pipelines and showing why using pipelines is much better than writing just sort of sequential code. Okay, and here we import these two base classes from scikit-learn, transformer mixin and base estimator, in case we wanted to create our own data transformers. Now from feature engine, if we want to apply imputation, then we can import categorical imputer, adding missing value indicator and mean median imputer, and also to apply encoding. So if you have a rare label, okay, maybe you have a categorical variable where some of the categories are quite rare in the data, you can combine them all under one category, and also one hot encoder where you can represent categorical data numerically. And here we download the data from this GitHub repo. Just in case the data has missing values, sometimes people use question mark, we replace them with a numpy-nan. This is the Titanic data, okay? And then what we do here is we look at the column called cabin, and we take only the first letter of that column. And here, from the passenger name, we can get the title, if it's Mr., Mrs., Miss, Master, and so on, which is we grab the title, we add the title as a new column, okay? Sometime later we can drop the column called name. So if you download this notebook and run it, it should run for you. Okay, so we remove unnecessary or unimportant columns like passenger ID, name, and ticket. And here, this is what, if you remember, I mentioned configuration, that the columns age and fare are numeric. So I need to make a note or save some configuration to say that, yeah, these two columns are numeric, and these columns are categorical, and that we need to pay attention here, for example, to the cabin column. Okay, this is just an example. And now here what I do is I split the data into train test splits and then apply some pre-processing. So what I do here is, instead of writing a simple function to extract the first letter from the column cabin, I write it as a transformer. Okay, this is a transformer based on the base estimator and the transformer mixin from scikit-learn. This way I can include this stuff into a pipeline. If I leave it as a simple function like this, it's not going to work. Okay? And now I can create a pipeline. So what I do is I can, for example, impute categorical variables. So if any categorical variable has a missing value, I can replace it with a word missing. I can also add a binary missing indicator to a numeric variable with missing data. Imagine you have a numeric variable with plenty of missing values. I'll add a new column and then put 1 if the value is missing and then 0 if the value is not missing. I can fill NA, for example, or impute the missing values with a median value, extract the first letter from the column cabin, group rare categories, perform one hot encoding. Now my data is numeric, so I can scale the data and then fit logistic regression. This is what this pipeline is doing. So categorical imputation with the word missing, add a missing indicator to the, see here, that's why I have the configuration for those columns, because I know I can say apply this to these variables. That's why even the variable names are in capital, to say these are constant. Right? Then apply, okay, extract the letter, median imputation, apply array level encoding, and the tolerance is 0.05. So if the category makes less than 0.05 of the entire column, then put it under the category called rare. And now apply one hot encoding to the categorical variables, and then apply data scaling or standardization, and then train a logistic regression model. Now I can fit the model. I can save it into a file. This is how you reload, you save the model and reload the model using joblib. This is the entire pipeline. And now after you've reloaded the model, if you wish to visualize maybe something, you can do that. But after you've saved the model, you can reload it and use it to make predictions. There might be a typo here in my code. I'm using the Titanic pipeline, which is the trained model, but I should have used maybe the loaded model, because I'm assuming that we have saved the model and then in the future we're reloading it and using it to make predictions. So you can correct this. This should say loaded model rather than the Titanic pipeline. Okay, so this is in the research environment. Okay, here at the bottom, I show you how to create your own transformers, but this is beyond the scope of this course. I'll leave this for the future. Like, for example, the mean imputer, rare label categorical encoder. We do have them in the feature engine package, but just in case you wanted to learn how to write your own transformer, this is how you do it, with the fit and transform methods from the base estimator and the transformer mixin. Like I said, we have a full course on these things with O'Reilly, so I'd like to invite you to join that course if you're not familiar with this stuff. Right, so I want you to pay attention now and have a look at this code, right? And in fact, so let me go to where the code is. Okay. Go to where the code is, and then load Spider as my IDE, so that we can have a look at the code together. But what I'm going to do now is I'm going to show you how we map this code into this package structure, which is basically similar to this. Okay? For example, the model, test, requirements, where everything goes, and so on. Okay, let me have a look and make sure everything's good. Super, I can see some questions coming through. Please keep them coming and we'll try and address them together. Okay, like I said, remember this is being recorded, so in case you think I'm a bit too fast for you, remember this is being recorded. So let's go to the code and we'll try and address it together. Come on, come on, come on, come on, come on. You can probably hear the fan on my laptop working really hard. Okay, so let me go to where I have the code so you can see everything we do online. Let me go. Yeah. It's here. It's here. And then, so let's go to classification model, okay? Yeah. Can I open? There we go. So this is the package structure, okay? I'll show you what this means as we progress. But I wanted to have a look at Titanic model, okay, and see where I put files. For example, the dependencies and importation and so on, these can be put anywhere, but I tend to put them, for example, under maybe, let's have a look, so in the beginning, if you have any data, we put it under the datasets folder. Okay, that's the raw data.csv. And if you have any configuration, you might have spotted config. So we have a config folder, and there I have a Python script that has this configuration here. Now, this configuration is coming from the package called pedantic or pydantic in Python. Okay, and this helps you model your problem and create the configuration. For example, this is what we call application level configuration, where you can add package name of type string, raw data file of type string, and then the pipeline save file of type string. This is so that you know where to save your pipeline and where the data file is. And then the package name, these are all of type string. And then here, this is configuration relevant to the model training and feature engineering. So the target variable is of type string, at least the name of the variable is string. If you have any unused fields or the features are sequences, the test data size is of type float. Random state, remember when we spoke about reproducibility, so random state is to fix the random seed. If you have any numerical variables, categorical variables, and the cabin variable. Okay, remember we put them into capital variables there. Now we add them to our configuration. Okay, and now this is basically a master config object. I'm assuming we know Python and Python OOP. It is a simple class. And then here we have a few helper functions that can help us find, for example, the configuration file. And notice we're using Python type hints here. I don't know whether you've seen this stuff before. So this is of type path. And you see that this is coming from the path lib. And then the type sequence is coming from the package called typing. And even when we deal with the YAML, we have a nice package called strict YAML in Python. Okay? And by the way, something I didn't mention here, we put our project directories. Okay, so for example, the package root folder, the root folder, the configuration file path, so where to find the config.yaml file, where to find the datasets file, and where to the datasets folder, and where to find the trained models folder. Okay, and these are, like we said, helper functions. Okay, like we said, we have provided plenty of explanatory comments so that it makes sense. Now, for dealing with the data, you can go to, that's the config. And by the way, you can see the config here is done in a YAML file. It's not a Python file. This is because we want to reduce the power of these files. So because a Python file can be executed, whereas a YAML file is a plain text file, then whenever you can, always make sure that you use a plain text file. Okay? So this is the package name. Notice these are configuration variables, okay? Package name, we'll call it Titanic model. That's the raw data file. If you want to split the data into train test in advance, it's fine. You just put the file names here, okay? The target variable is called survive. The column is called survive. That if you have a look at the raw.csv, you'll find it. And then these are the features we have. Oh, sorry, the pipeline name is Titanic classification model. And then the saved file, this is where we later on build the model and save it. We'll give it this name and then a version number. Now, where we save it, remember the config here, we'll save it under these paths. Okay? Under this path here. And this is where we find the data, and this is where we find that config.yaml file, which is this one. I hope you can see the link between coding these things into the package so that the package automatically finds any file it wants. Okay, that's for configuration. Like we said, if you have data, then you can create a data manager file if you want to apply anything. But here we're going to do the split on the fly. So we'll split the raw data file into train and test. And you might have spotted in the config file, in the YAML file, that we specify the test size and we specify the random state. This is to guarantee reproducibility. Okay? And then we know that these fields are not used, so we'll hard code them or I'll list them in under a category called unused fields. These are the numerical variables, age, fair, and so on. These are the categorical variables, sex, cabin, and so on. And this is the cabin variable. This is a variable that we'll have to pay attention to because we want to extract only the first letter of the cabin column. Right? What else do we have? Now we spoke about the pipeline that we have looked at on the Jupyter Notebook. Now that is saved under its own Python script. This is the same pipeline from before. Okay? But here, notice, we do the imports that we require. And notice we also import the config from the config.core, and also we can also, for example, import our own transformer. Okay? So any preprocessing, by the way, is saved on this column, this folder called processing. Okay, so data manager dealing with features and applying validation. So if you look at the data manager, for example, here is where, for example, we have those functions in case we wanted to prepare our data. This is where we save the pipeline here, okay, and we load the pipeline here. Okay, and as you can see, we have a helper function here that when we want to save the pipeline after we apply training, we delete any existing pipelines and then only save the most recent one. You can have a look at features. This is where we write our own transformers. Okay, so from typing, for example, we can import list, import pandas, import base estimator, transformer mixin, and then write our own transformers. Okay. At first, this might look a bit complicated, but this is, like we said, a professional way of packaging up your model. And then you can apply validation here, for example, and these are also almost like using what we call schemas. Okay, so for example, the P class column is of type int, the name column is of type string, the sex column is of type string, the age column is of type int, and so on. So it's like almost like schemas. So this is one record in your data. This is when you feed the data into the model. This is one record. And now if you wish to maybe send the model a full data frame of data of records, then it's a sequence or a list of these schemas. I hope the idea here makes sense of using the schemas. Okay? You have the base model from Pedantic, and then you define your data schema, and now you have the inputs now is going to be a list of these guys, because you have multiple records in your data, and each one of them represents each record should adhere to this schema. Okay, so let's go back to our pipeline. These are the imports. So from feature engine, we can import, for example, one-hot encoder, rare label encoder. We can import these guys for imputations, and we can also import our own transformers. And then remember, we import the config, so because we have everything inside the config. See now, instead of hard coding the column names or the variables, we can call them from config. Remember the numerical variables? We saw them under config, YAML, these guys. That's how we professionally call them under your pipeline. Okay, so you don't hard code them here to cut down making mistakes. So you only need to update the config file if an update is needed. Okay? And then this is where we apply training. This is where we run the training. See, it's in a separate script because of software engineering standards. Remember, we reduce everything into one purpose. So every script does one purpose. That's why it's broken down into multiple scripts. Okay, this is where we apply the train test split. We get the feature names from the configuration, the target variable name from the configuration, even the test size from the configuration, and the random state from the configuration from this YAML file again. There you go. Okay? And then you can trigger training. And then the train model will be saved here. Okay, these variables will not exist. These ones is just because I've run training before. Usually, let me actually go to the folder. Okay, I go to the folder. Usually, you will have, so you won't have this. Okay, you can delete this side. Keep requirements, keep tests, keep the model, and then also you don't have this. So you only have requirements, test, and Titanic model. The requirements folder, by the way, the requirements folder, where is it? Here. Yeah, the requirements folder will contain text files that contain requirements. As you can see, if I zoom in a little bit, I'm specifying versions that we're going to be using. So numpy between this version and this version, pandas between this and this, pedantic, scikit-learn, strict YAML, Romal YAML, feature engine, and job lib. Later on for testing, we'll need these packages, okay? We'll need the package called black for code styling, flake 8 for linting, mypy for type checking, and then isort to make sure our imports are in the correct order. Okay, this is, like we said, professional Python stuff. So we pay attention to everything, even to the order of importation, package importation. Okay, remember type checking, flake 8 for linting, and then black for code styling. And then we're going to be using the PyTest for testing. Okay, so please pay attention to this. Take your time when you study the structure of this package. I have to say, it might be new to you. It might be something you've not seen before. Take your time when you actually study it. Okay, so let me go more into this stuff. So the setup file here is quite helpful, and this is where you specify details of your package. Now you might say, and please pay attention here, you might say, oh, this is very advanced, this is too difficult for me. I'm going to tell you something that's really useful, and that is, you don't have to write anything from scratch, because you have access to this code, so you can customize it to your package. You don't have to write this stuff from zero. Okay? So you don't, please pay attention, you do not have to write this stuff from zero at all. Okay? You can use this stuff, for example, change the URL, change your email, change the author name, change which Python version you want, and then these are just configurations, for example, for the root folder, where the requirements are, the name of the package, where the model is, the version file, and so on. And you might have noticed that we have under the Titanic model, we have a file for the version. So we can add a version here. Now I'm in version 0.0.10. Okay, and this is something I wanted to learn, what we call semantic versioning in Python. Okay, we have 3 fields, what each field means. Okay? Please pay attention to this, how to professionally package your Python code. Okay, let me close these files. We have so many open here, and then we'll come back to any of them whenever we need it. Okay, so I hope this makes sense. How to map